The next part of this section, we are going to talk about how to graph complex numbers. So we're going to use the complex plane, and a plus bi is graphed like a point. So we would take whatever a is and whatever b is, and we would switch it to be in point form. So that means that we're actually going to be changing what our axes mean. So our x-axis is now going to represent our real axis, and what is normally our y-axis is going to be the imaginary axis. So if I wanted to graph our complex number of 2 plus 3i, this is really the same idea as graphing 2, 3. So I'm going to go right 2 up 3 and put my point. So 2, 3, here's my point. I'm going to label it as A. So same thing, so this is going to be negative 1, 2. So when I graph it, we're going to go left 1, up 2. So there's B. And then this one, since we don't have a real part, our real number is 0, and then our imaginary part is 5. So we're just going to go up 5 and put our point. So that's how we would graph. Now on a graph, we are thinking of these points as something called a vector. And a vector is a line segment from the origin to the point. So as we're graphing those, we're really thinking of it as this point, connecting it back to the origin. So this right here, this is called my vector. So even this direction, so this is my vector here, and then up to C would be our other vector. Now the length of our vector is called the magnitude, okay? And our vector also gives us a direction. Okay? So to find the magnitude or the length, we take the absolute value of our complex number, which is really the same idea as using our distance formula. Okay? So the length here, so again, when we take the absolute value of a complex number, we're really finding the length of this vector. And this is our formula for doing that. So again, we're thinking of it on a graph. So on a graph, the vector is really a line segment, and we're finding the distance of that line segment. Okay. So if we do practice, so we graphed the 2 plus 3i already. So now we're going to go through and we're actually going to find the length of this vector using our absolute value and our distance formula. So if we're going to find the absolute value of this, so again, this is our a, this is our b. We're taking the square root of a squared, so 4, plus 3 squared. So that would be 9 if we simplify right away. So that's going to be the square root of 13. So this has a distance up here. So this length right here is a distance of 13. Square root of 13. Same thing for the next one. If we're going to take the absolute value, we have a and b. So negative 1 squared is positive 1, and then 2 squared is 4. So this is going to be the square root of 5. So again, on our graph, this length of our vector is the square root of 5. And our last one, so again, taking the absolute value, we don't have an a, so that means that's just 0. And then 5 squared is 25. So the square root of 25 is 5. So really that's probably the easiest one to see. So again, if I go back up to my graph, since we already graphed it, if I just count up 5 spaces, so 1, 2, 3, 4, 5, that's the length of my vector. And I found that taking the absolute value, which in complex numbers means the same thing as using our distance formula. Now when adding complex numbers, we are adding our vectors together and combining them into one vector. And when we're multiplying complex numbers, you are scaling and rotating a vector. Okay? Now these can be very useful tools, and it's a useful understanding when you start working with polar coordinates, which in the real world, I guess that would be how planes would navigate, or even ships would navigate. They use polar coordinates. So, but we're going to talk about what I just said graphically here. So again, if we are graphing, again, this is our real axis. This is our imaginary axis. So this point right here at the tip of that arrow is going to be at 2, 3. So which really means the same thing as 2 plus 3i since we're in the positive plane. So now let's say I want to take this vector and another vector. Okay, so again, this was my 2, 3. So it really means 2 plus 3i. And I want to add this vector to it. So this vector is at 1, 3. So again, this really means the same thing as 1 plus 3i. So if I just want to add those algebraically, so if I take 1 plus 3i plus 2 plus 3i, that is going to give us 3 plus 6i. So what we're doing is we're actually going to take this vector, and without changing its slope, we would pick it up, and we're going to put it right at the front of this vector, or I could do it vice versa. But again, that slope is going to stay the same. So a picture of that. So if we call this one vector A and this one vector B, here's vector A, and we're adding B to it. That's going to give us our new vector. Same thing, this was our vector A, or we could add vector B to it. So the order that we added, it's not really going to matter. But let's double check to see if we got this 3, 6. So remember, as a point, this would be just 3, 6. So on my graph, I'm going over 3, and I'm going up to 6. So I get 3, 6 here, which again is our 3 plus 6i. So geometrically speaking, when we're adding vectors or adding complex numbers, this is what's happening. Okay. And that is also going to conclude section 4.